am a biologist by training. I have a PhD in biology, and I went on to be a data scientist from the academics. And I think there's an incredible opportunity, just to pitch, an incredible opportunity right now to give data science to everybody. And there's a ton of data out there. We all know this. We've heard this for 10 years. And there's a ton of uses for that data. And what I'm trying to do is make tools that make that data accessible. And I'll start with the first project that we did, which is called Biopredictor, and tell you how that spun off into a number of other projects and some sort of passion, personal projects that I think are going to become generally useful for everybody in the world, I hope. But it all centers around graphs and Grakn in particular, because this I believe is one of the keys to making this happen. Having a very rich representation of knowledge that's accessible in an intuitive way. So after I tell you about Biopredictor and what we tried to do there, I'll tell you how I think we can enrich Biopredictor and many other things using Grakn to bring it full circle. So let's see. Yeah, so this is basically just what I said. A lot of today's data is hard to access and utilize and derive insight from. So we've got access to public data sets. We've got legal access to many rich data sets, but to actually get insight from it is very hard. And that's not because there's any legal barriers, it's just because there's actually intellectual barriers and technical barriers to this information. They're bound up in big tomes of spreadsheets and whatnot, and that formatting is not particularly useful for regular people to understand. So there are a number of challenges. I'm going to just use my finger, I guess. Does anybody have a laser? Do we have a laser? All right, I'm just going to point. So data management is one of the issues, right? So getting data from the place where it's in its data store to something that's a little bit more useful is one issue, right? And maybe you take that a step back further. Are you cleaning your data is obviously a huge deal, right? Compiling data is a huge deal. But there's also data analysis, and that's sort of the step I focus on is data analysis. How do you, once you have clean data, once you have data that's stored in some sort of reasonable, accessible manner, it's really not done, right? Because you can give that to anybody and most people won't know what to do with it unless they're very, very, very familiar with that data, right? So how do you get to the analysis step where you can actually analyze the data and get usable insights from it? And then which usable insights do you use, right? The Grakn knowledge graph is going to help bridge that gap. So the three data stories I'll talk about today are Biopredictor. Biology is a deep technology domain, so this is a new term, deep technology company, where you've got technologies that you need a lot of expertise to actually get any value from. There's many, many layers of barriers to actually deriving value in biotech. The projects are ambitious. If you look at any of these projects, a lot of them, are not particularly likely to succeed. There's a lot of technical barriers to any of the successes in any biomedical project. The complicated subject matter, obviously when you have to have a PhD to understand or to drive one of these companies, there's complicated subject matter. And then the funding is very high stakes. So funding that's in biotech is particularly risky. You can get a lot of return on your funding, but there's actually a lot of failures. So the second part is, so I'll talk about Biopredictor, then I'll tell you about the collaborations graph. Underneath Biopredictor, after we profiled biotech companies, we were interested in looking at what drives biotech, and that's people, right? And it turns out that in biology we have an incredible data source that's robust, reliable, and public, and that's our publication record, right? So people, as a matter of course, to develop a career, have to publish, right? And that's a indisputable form of behavior, right? It's an indisputable record of somebody's behavior. So I'll talk about the collaborations graph that we made to enrich the biotech analysis. And we look at collaboration patterns and clusters of domain knowledge was a particularly interesting thing to look at. And then the cancer graph. So after doing a lot of this work and thinking about how I could actually make something usable and something useful, I started to ask myself, there's a gap, right? So I know that there's a lot of need for data science, and I know that this stuff is supposed to be really valuable, right? I could be a contractor for a company, I could teach data science and do both of those things, but there's something missing, right? So I spent some time sort of soul searching and thinking what's missing? I know there's this big hole and I just don't know how to identify it, how to fill it. And I said, okay, wait, maybe my friends and my family have stories that they need data science to fill. You know, they have needs, and data science can fill those needs. And if I talk to them about those, like, what are your pain points? Can I find a product that would fill that? Right? Can I find a product that would fill the pain point? So I started just that intellectual change about, like, you know, sort of talking to people and saying, what's your pain point? Brought about, like, a lot of ideas, and I'll tell you about one of these ideas. It's a personal story. One of my relatives has cancer, and she has all these ideas about what the literature says, right? But it's not really what the literature says, and how could I help her bridge that gap, right? So that's one of the types of products that we're trying to focus on, right? One of the types of ideas. So that's everything in a nutshell. And then this is just what I was talking about. Austin Capital Data. We try and educate, enable, and build analyses that allow people to bridge the gap between the very rich data sets that are out there and their own problems in the world, right? And I think, again, I'll say it again, I think knowledge graphs in general and Grakn is a very good way to build an intuitive analysis. I can go into these data sets in a little more detail. So the biotech company data set, it has information on the leadership. So we scraped the web, we got information on leadership in 6,000 biotech companies. What tech domain, what geographic region, what's the funding history of these companies. So we have these types of features in the data set. Collaboration networks is coming, so that's coming from the web. Collaboration networks is coming from PubMed in particular, and it makes it very easy to just scrape papers and pull pieces of them apart. I'll show you that in more detail. And they have information in, you know, if the person's a scientist, we use this for a scientist businessman classification. So we loop back into the biotech startups, and if they have a PubMed footprint, they're a scientist, and if they don't, they're not. I know that's kind of general, but that's how we were able to do it easily. And then who are their collaborators? You can pull this right off of the paper, right? So that's really nice. Paper titles was the first thing we analyzed, so we could get some information about what these people say they know, right? What people publicly declare that they know from the titles. We dig a little deeper in some other analysis where we get to the abstracts, but you probably do the whole paper. Titles is easy, obviously, or the easiest of the things we can do, and relatively reliable. And then the cancer literature, right? So we used NCBI and PubMed and BioPython to get cancer publication data in particular. What this really is a richer subgraph of PubMed, right? And the goal for that is to make this literature accessible. So we've got keywords, abstract text, authors, and the chemicals, also mesh terms. Yeah. Oh, thanks. Appreciate it.
Click on it.
All right. Got it. Fantastic. And then these are stored in graphs in Grakn, so we can analyze them relatively dynamically. Okay, so again, this is the first talk. Let's see. This is the first thing. So the biotech startup graph actually started as a capstone for Berkeley Mid. So me and another person, Dennis Voljadak, who is talking here as well, were teammates at Mids at Berkeley. And we wanted to understand biotech startups, and we built this project out. So you can actually still see this in its original form, and we have a web app that you're looking at right here. It's a shiny app. So we predict biotech's success. This is the expected valuation. You can see this odd distribution. Most companies fall here, right? But if you're really interested in this, you can actually explore this and pull out the company names and look at their features. Okay, so biotech investment is risky. At this point, there was 1.5 billion being invested in quarterly. Cumulative investment was 62 billion, and then the gross returns are higher than that, right? But they're not that much higher, and only 11% from the first data set that we were looking at, just a public discussion of this, reached any liquidation event at all. So 90% of these companies were failing. In our data set that I'll show you, our IPO rate is 7%, so it's consistent with that, maybe a little bit less optimistic, but regardless, there's a high likelihood of failure if you're investing in biotech. Here's another analysis that you see, and I just want to point out that 44% of these deals resulted in loss, right? full or partial loss. That's a little bit different, but it also shows that there's a lot of loss of money. So the question was, can we just look at the features, mask the IPO, look at the features and see if these companies were IPOs or not? And that was the basic project. And the first question is there actually a signal in the data? Is there anything usable? So, so we looked at the features of interest, the company, the staff, and the general market, like which market they're in, and we pulled out those, another subset of features. You can see a very sort of cartoon version of this. So we've got biotech company data here, leadership, tech domain, geographic region. So sort of summarized in the other slide. And then PubMed data was folded in to split these guys between the leadership, between science and business staff. We put all of that in a NoSQL database, and then did some machine learning on that. And so this is the basic architecture of this analysis. Okay, so is there a signal? What do we see? Well, you can see that IPO time is decreasing. So of the companies that have an IPO signal, by 2015, IPO time, so this would be days to IPO, right? So it's dramatically decreasing. That's a trend that we're seeing. So there's something going on, right? So you can look at biotech in key cities. So this, I'm sorry, this is blurry. This is the total amount of funding, right? So the size of the circle is the total amount of funding, and you can see there are key cities that have the majority of biotech funding. So if you're interested in, like, starting a biotech or going to work for a biotech, these are probably the places you want to go in terms of amount of funding. The median dates to IPO is kind of more interesting because some of these places that have less funding have very favorable. So large and green would be favorable, right? So the median days to funding in some of these places is actually low, even though they don't have a very high investment in biotech in terms of total dollars. So I think, this is the drug corridor right here in New York City, New Jersey. So that's your Pfizer and all your drug companies, I guess, drug startups and stuff. I think that's what's over there. And then there's other places in the country that appear to have IPOing biotechs without a whole lot of funding. So that's another interesting fold. Okay, and then some more of this decade level funding. So years to IPO, you could see the general trend that's going down. From this, it looks like there was a pulse in funding a couple decades ago, and then there's still more funding than before, right? We're relatively flat, but as time goes on, it looks like the bubble sort of burst, I guess, right? So that's closer to current day. And then one of the sort of most digestible results was we were able to show with this split between companies with greater than 50% scientists and less than 50% scientists. And again, this is just defined by their footprint on PubMed, if they've published in PubMed. If you have more than 50% of your leadership staff that has that footprint, you IPO faster, right? Measurably faster. And there's a lot more companies that don't fall into that category, and IPO is slower. So I think that's probably the easiest take home. And then we also showed that you could split by city. So we know that city is important for biotech, and we wanted to just look at the characteristics of these cities. So this pulls back a little bit from, just basically showing you that we have a signal and that some things are happening. And we're trying to say, okay, can we say something more general about cities across multiple features, right? So this over here would be percent IPO and percent scientists in the company, right? So it's not split 50 or not, it's percent scientists. So in San Francisco, we can see the characteristic of this city is we have percent IPO is relatively low compared to the other ones, but the number of scientists in the company is relatively high. So those are it sort of matches our stereotype, right? At least this part. We've got people who have all their technical degrees being attracted to this hub of innovation, right? So that's kind of interesting. San Diego's a little different, right? We do know that San Diego, at least from reputation, San Diego is a major biotech hub for established companies, and they show that they have more IPOs. Austin has even more IPOs, I guess, and percent scientists. I have to say that there's just not that many biotechs in Austin, so that's really not representative. There's probably, 5 5 or something. so I only put that in there because I live in Austin, and it looks really good, but it's not particularly. These are much bigger powerhouses. All right, so, and then some more stats, right? The percent IPO, companies reaching IPO in less than 6,000 days. So the national average is 16%, right? And then the national average of percent scientists is 21%. So actually it looks like San Francisco's just around average, and San Diego's above average. So if you want to go to biotech, maybe San Diego's probably the place to go. Okay, so I'll talk about our machine learning analysis, and I know we're a little bit tight on time. I want to get to the end of the talk, which is sort of the punchline. So I'm going to pick it up a little bit. Let's see. So we tested a range of machine learning models. This is your standard machine learning pipeline. We tried all different types of models, right? We tried regression-based models, discriminant analysis type models, and then decision trees. Okay, so we have every type of model that you can sort of think of, and then we looked at the harmonic F1. So what's the result in predicting the IPOs? So if I mask my data set and I ask, are these IPOs, which of these models works the best? We get a very clear result where logistic regression seems to work very well, right? And I would favor logistic regression because it's transparent. And then your decision tree, which is also sort of transparent, is also working very well. But your other, I guess you might argue, fancier models, discriminant analysis, SVM, is not working quite as well. So that just tells you that we can predict this with relatively good F1. I'll show you those results in a little bit more detail, so we can talk about what we're getting and what we're losing from this prediction. And then I'll go and jump into graphs, because I know that's why you guys are all here, and I don't want to bore you with machine learning. So here's our confusion plot, and just to familiarize you, this is the true label over here, and this is the predicted label. So this is yes to true and yes to predicted. That's a very important chamber over here. This would be where our model said, yes, this is IPO, and it was actually not IPO, right? And this over here would be, it says this is not IPO, and it actually was, right? And I should highlight that says 71%, right? And then this one over here is no IPO, and it actually wasn't. So this is a true false, this is true positive. That's actually what we're looking for, are these true false and true positive chambers. Okay, so what I should point out is that 664, so this is a subset of filtered companies. I said 6,000. After we got done filtering them, there was about 1,000 left, right? So because there were a lot of issues with the data integrity and whatnot from this web-derived data. But 664 of these roughly 1,000 companies were not IPOs, and we could say positively that they're not IPOs. So that's a true false. We truly predicted that this was false, right? That's what that is. So you could actually ignore these companies using this tool, and that's a big savings if you're an investor. Now these are the things that our model said were IPOs over here, and you can see that we've got 14 companies over here and 70 companies that I guessed wrong at. So you may or may not think that that's good, but what I want to do is bring out the fact that if we focus on this 14 companies, we can capture 30% of all of the true positives, right? So you go from having a 7% true positive rate to a 30% capture rate, and you're only focusing on 14 companies versus 1,000 companies. So it's a big difference in investment. So this is our sort of our value statement for this analysis. That if you use this tool, you can hone your analysis. You can cut out the large majority of the chaff, and you can focus on the companies that are really going to be winners. And we can use this plot that's just feature importance, right? And you can see the rough analysis of what these features are. So we've got scientific features, tech domain features, and company size. It turns out that the relationships in the company, that feature is really important. So it turns out that perhaps, perhaps it's really important that we have information about relationships. Okay, so I'll just, you see that analysis. I want to jump to the meat of the talk. basically, I don't know if you guys are familiar with this. This is 23andMe, and this is Theranos. The model can't tell the difference between these two companies, and that's a big issue, right? If you're familiar with this, 23andMe is a very well-founded company with a lot of smart people in it and a very good idea. And Theranos is full of at least one person who doesn't really know science and thinks that they can talk their way through it. And I think it ended in some bad outcomes. But anyway, regardless, the model should be able to predict this difference, and it can't. So this is a flag. That brings me to this. We can get more with a graph, right? So I believe that, I showed you that relationships in the company are important. Scientific record is important. We didn't really bake that in here. We just said, are these people represented or not, and how many of them are represented? So what we really want to do is get like a richer view of what's actually inside those companies. So from that, we moved to our analysis on PubMed data and looking at relationships and collaborations. If you look at what a collaboration network looks like, this is my postdoc advisor's collaboration network. This is just secondary collaborations coming from papers. So, so she's in the center. These are communities of people connected to their papers, so that's why it gets so cauliflower-like. But you can see how fast a secondary network can grow out of a collaboration analysis. In a typical analysis, we judge scientists by paper count, journal impact factor, and citations. I believe this type of analysis will do much better than that because it's much more rich. You can actually, so the question is like, you can look at like paper count or something and you can look at whether this person's published or not, but that may not give you information about who that person is, right? So what's their true expertise, and then what is the network expertise? Those are the questions that we can get out with a graph. And I believe those things are much more important for like how well this person's gonna do. Again, it's a rich record of behavior. It's a long-term record of performance. It records alliances, and it records expertise in a publicly declared manner. So you can look at a paper, and we can break it down into pieces. You've got journal type, journal reputation. The title of the paper is very telling because it's their public declaration about what they're talking about. Collaborator list is what we really dug into. And then company and institute, like workplace, what's the geographic location. And then there's a lot of things we can dig into like with that, but that's even more blue sky stuff. So we took the PubMed database. There's 24 million papers, so that's a lot of data because it's not just a data point, right? It's 24 million very rich documents. 1.5 million of these are open source, so you can get the entire one. You can download it as an XML file and then parse it, which is what we ended up doing. So this is a slice of the PubMed data set. Call that open access. This is the basic setup. You've got a focal person, a primary collaborator. So here's a paper, here's a paper, here's a paper. You can go out to about third degrees without really blowing up. Second degree is probably more usable. But anyway, this is the idea. So you've got publisher, scientist, and 3 papers would connect those people, right? And this is what it looks like in Grakn. So this is just a slice with a limit. That's why it's not really blown up. But this is Colleen Murphy again. That's my postdoc advisor. These are her papers. These are her paper titles. This is another collaborator with paper. Now there's another paper. And then these are actually other people, right? So there's the secondary network there. Secondary network here, and then that's the paper that links these people, right? So you can see what it looks like in Grakn. Okay, so the question was if we could identify stars using this data, and what I did was I sliced out the number of citations from these papers, and I found these 3 people, and it turned out that they're all important. You guys might be familiar with George Church. He's got 63,000 citations, right? And he's one of the genomics revolutionaries. There's these other 2 people who have smaller footprints, but they come out very prominent in this data set. William Paul Burns and Ian Clark. He's got 167 citations, but is very focused on mobile technologies. That kind of makes sense in this domain. Perhaps he's some sort of a domain expert. Ian Clark is similar. He's got 3,000 citations, so pretty respectable for anybody, but he's not George Church, and it looks like he's international relations. So again, in the business domain, this makes some sense. And you can see that these people hold higher than average number of positions across the boards of these companies, right? So George Church comes out at 7 companies, William Burns at 5, and Ian Clark at 3. And normally people are usually on the board of 1, right? Okay, so that tells me that we're looking at something maybe interesting. Another way to analyze this would be to slice out the top publishers, right? So we just stacked these publications up and then looked at who published the most. It turns out that the published the most. It's obviously a data integrity issue. Gunnar Eisenbach, who I had never heard of, but it turns out I should have. He's the top publisher of humans. And then Hong Kong Fun and Seng Keng Ning are 2 very similar numbers. They come out of very similar numbers. And again, these numbers, well, I guess 2,000 publications is very odd, right? It's very high. But these people probably published more than this because remember, this is a slice of the PubMed data. It's a public slice. So the signature is worth investigating. You can look at their networks. I just got these pretty pictures from Gelfi. We pulled out the data and put it in Gelfi. Gunnar Eisenbach has this very distributed network with sort of nodes and communities that expand this way. These 2 guys actually cluster together, which is really interesting. You know, that's the first story that came out of that. And their networks look really tight and not connected at all, right? So the thing that this was kind of an interesting result. You know, I guess the result is that we can traverse through this network to get to these two communities, but the communities themselves are not that interconnected. Okay, so Gunnar Eisenbach is indeed a star. He has something called the Healthcare Nobel Prize, which I had, again, never heard of. I guess I should be embarrassed about that, but I'm kind of happy that I learned something I should have known through my analysis, right? He invented a field called infovalence or infodemiology, which is probably becoming more and more important. And basically his idea was, I can look at Twitter, I can look for things like sneezing and feel bad and headache, and I can chart epidemics that way, right? So basically I see if people are tweeting about their health problems, and I can build real-time analysis out of that. So that's infovalence. And that's what he got. And I guess it says one of the most productive researchers and publishers online in the health field. Okay, so that's a big deal. Now, if you look a little deeper, there's actually something wrong with his network. His co-authors, he has a lot of people who he doesn't co-author with more than once, right? So if you look at this network a little different, you've got all these papers, and then you've got these few co-authors, and they're not highly interconnected. So there's something odd. All right, 5, okay. All right, so I'm gonna, so we can dig in a little bit more, and you can actually go to the secondary network, and you can see these co-authors are linked only once. There's something really strange. It turns out that if you dig in deeper, the analysis was coding his editorships as authorships, and that was another data integrity issue that we pulled out. I'm not sure if this is a win or a loss because we sort of screwed up the analysis or somewhere, but then we found out, you know, something about somebody important and something about a different network type that we can pull out automatically now. These guys are the true, Fong Ke Hong and Sen Ke Wek are the true stars in this, and they've got what you expect. A lot of co-authors and a lot of papers. I should say that the surprising thing about this as well, let me say this, is they've both co-authored greater than 2,000 papers, and they're both X-ray crystallographers in Asia who don't talk to each other, right? So I mean, it makes sense that they're very similar. And this is just a statement about, you know, how important this guy is, right? He's highly collaborative. Apparently he's not highly collaborative with this other guy. So yeah, they're both the 2 biggest publishers in X-ray crystallography, and they publish structures and they're very important. Okay, so I think I have a few minutes left. I'm just going to blast through this. These are 2 other networks that are personally important. I study C. elegans. This is my postdoc, my postdoc advisor. This is my my PhD advisor. You can see how different these guys are. What I want to point out is just the topography is initially, like as you look at this, you can see these are different people. They're both highly established, but there's a lot of information in there. And I think it's relatively accessible. I'm going to go past all the analytics that we can get to and just tell you my punchline because I know we're running low on time. But there's a number of things we can actually pull out quantitatively from these graphs: paper counts, triangle counts and wedges. We can traverse the graph and see how fast their networks blow up. I'm sorry I'm going through this really quick. I'll give you guys the slide deck through Grakn. And then grass traversal patterns, right? So that's the triangles and wedges. And we can also pull out word clouds, or this is sort of a popular way to do this. You can do this in bar graphs as well, but I mean, you can see that Colleen Murphy studies aging, longevity, and genes, right? And you can do this at different levels, right? It gets a little bit more messy if you look at her other networks, but we can pull this right out of the title. So you can do NLP on them in the title and see if people are doing what they want. And this is just to show you, I can get a full suite of analytics off of her graph. All right, so let me just jump forward. These are word clouds from cities, so we can actually characterize cities, and it comes out very clearly that San Francisco has a lot of emerging technologies. If you look at these words here, when you look at the deck, they're all emerging technologies, and they're not a lot of representation of anything except cell. Austin is lung cancer centric. It actually is a cancer center. The Lung Cancer Journal, the Journal of Lung Cancer comes out of Austin. That comes out. And then Vicinia virus in San Diego, right? So there's the Vicinia Virus Institute in San Diego. I'm not sure if that's exactly the name, but it's the institute that studies that. This is just more about how you can pull out information from these knowledge graphs. So what I'm saying is that biotech can be targeted, biotech can be analyzed with machine learning, and then with the graph layer, you can get way more information for recruiting, for if you're a biotech person looking for a job, if you want to leverage, if you're a VC and looking where to put your money, you can get all this information out of these networks and this intelligence system. Now, I want to talk about cancer graph. Just give me like 5 minutes of your time. I know you guys are all hungry, but this is actually the main point of the talk. So all of this work is sort of basic bread and butter data science, right? I mean, it may be in a different domain. We found some interesting stuff, but I think the thing that's really important about what we'd like to do is we'd like to bring data science back to people that we know, right? People that are in our everyday surroundings. That's a big hole. So like I said, my sister has pancreatic cancer. And this came after I sort of started thinking about this, and I said, well, is there anything I could do for her as a data scientist, right? So this is Tracy. And she's got a lot of people that love her and all that, and she has a lot of these benefits and everything, which is a normal thing to do when you have cancer, right? You have a benefit, you talk to your friends, they tell you, oh, my friend had breast cancer and they used this treatment, and I know about this. And so she gets all this information coming in, but none of it is actually scientific information. It's all rumors. And that's a shame when we have a huge body of scientific information that we've all paid for, right? I'm not going to say that this is like some sort of that the government is trying to keep us from misinformation. It's not that. It's just there's a technical barrier between us and that information. And there's a technical barrier between me and that information, and it's even more for her, right? It's even bigger for her or anybody else who doesn't have a degree in biotech, right? And that's not many of us. So what do we do? Is there anything I could do that could help her get actual information and make reasonable decisions? Now, I know her doctor does all this stuff, and that's cool. We can trust her doctor, but doctors are very overtaxed, and they have a set of protocol that they follow that everybody uses, and that's great. But as a data scientist, I wondered if we could do anything more. So I'll just leave it there and say. What I did first was I pulled all the pancreatic cancer data from PubMed, and I found 105,000 references, right? I can't read that. Here's the point. I said her doctor's probably already read all that, right? Or some of that, as a field, and made good decisions. But is there something more that we can find, right? And so I started digging in, and I said, okay, what I learned at MIDS, we're actually a library school, the School of Information. So we do a lot of social science. It said the most important thing with these data science analysis is you get somebody in front of you and you interview them, right? You figure out what's their problem. So I said, Tracy, what's your problem? What's the thing that you would most like to know? She's like, well, everybody's already told me how to treat it. I know about all the alternative treatments. What really is the problem is side effects, right? Like so in pancreatic cancer, we have a very aggressive treatment, and I get really sick, and I don't know how long I can keep on going to chemo, right? If I keep on going to chemo, I can do all right. But so I focused on that. I said, okay, maybe in those 105 references, I can pull out the side effect subgraph, right? And then start to look for clusters of thought that may be associated with side effects, and then I can serve just those references up to her. So that's the main approach. You can see the side effect subset. So I got 306 publications out. That's a lot better. I've got keywords, abstract text, authors, chemicals, and keywords again, I guess. And those are in a Grakn database. Let's see, so 306 is pretty good. What I targeted was what are the most important chemicals and treatments, and what are the keywords that are associated with those, right? So we can actually get to the entities in the graph and try and enrich using those entities. And then one thing she wanted to know, and maybe this is like, you know, are there any experimental treatments, right? Are there any centers of innovation that I can contact, that I can be an experimental subject on? And I think this is actually a very good use case for the graph, because you can see who's doing the best work. Key treatment strategies, that was one idea. I want to classify key treatment strategies. And then symptom management ideas, like are there any drugs that we don't know about that are, you know, that people are using in the literature? Either one of those things would be really good to know. This is the schema. So I don't know how clear that is. Basically, here's a paper. Here's the relationships to all the different keywords, chemicals, mesh terms, right? Here's a subgraph, right? So actually, the side effect subgraph that I'm focusing on right now has 7 papers, which is a lot better. And it turns out the 3 of these papers are highly connected, right? So here's the target right there. That's it. If I can get to those 3 papers, I mean, I know what they are, and get something usable out of it, then that's going to be a big deal, and I'll abstract that method to, you know, to get other information. Okay, so I promised you I would be done quickly. A lot of this work was done with BDSG, which is one of the companies that I work with Dennis Voljak. We're collaborators there. Kirsten Henderson actually did a lot of the groundwork, and Danny Woodka was our collaborator on the initial project. If you're interested in learning more about this work, you can join our Instagram feed. I've got a LinkedIn community that I work with, and you can look at austincapitalData.com. That's my site. So hope to see you in cyberspace and or afterwards, after the talk. Thanks.